Chapter 6 is getting done this week. This will be the end of week 5. That's different than typical. You have to get all of chapter 6 homework done by Sunday midnight, because on Monday we're going to have a test, and the test is going to be Monday 1 to 3. So you got to clear your books and make sure you're ready for your test, your midterm exam on Monday. And that midterm exam is going to cover chapters 1 to 6. So that's important because that's a big chunk of your grade. And secondly, because of just circumstances, I will not get chapter 6 covered during Tuesday and Thursday. I mean, I guess, but I would shoot through it. So what I do on Tuesday and then Thursday, you really need to either turn up on Friday and see the end of chapter 6, or at least watch the video of it that will be online, so that you can make sure that you've caught up on anything and everything you could be asked for. Well, so let's get started on the normal distribution. It's been found, this is a very remarkable property, but if you take data that is mound-shaped, right, a single hill symmetric, right, it's also going to be called now bell-shaped curve. We've already called it mound-shaped, and it's symmetric unimodal, which just means it's got one hill, right? Those three things are the same thing, right? They're just a different name for a hill like this that's nice and symmetric. So this is also called the normal distribution. So you got tons of names for it. Now, anyway, what was discovered about this is quite fascinating. They looked at the mean and the standard deviation. And they looked at lots and lots of different situations, like ages of people look like this. The heights of adults in America look like this. The scores you get in lots of tests look like this. The variation in blood pressure looks like this. They took lots and lots of different circumstances, and they discovered that they all did the same thing, which is remarkable. The first thing's probably not that remarkable. Do you know right at the middle where the hill is? That's where the mean is. And we're going to use that Greek letter, which you pronounce as mu. And that's the mean, right, of the population. And that's right in the center. I don't think that's too remarkable, right? Yeah, you'd expect that. But here's something that's less obvious, but also true. Do you know if you move one standard deviation away from the mean, right? And a standard deviation of a population is called that guy, and we call that guy sigma. If you move 1, 2, and then 3 standard deviations and back 1, 2, and 3, then every single normal distribution kind of has this shape. By the time you get to the end of 3 standard deviations, which is here. So if you take the mean, I'll do black. If you take the mean and you add and subtract 3 standard deviations, so that's basically here and here. So this guy here is 3 standard deviations, and this guy down here is 3 the other side. Then they found 99.7% of all the data lies in that range. Pretty much almost everybody. So if you take the average height of an American and you find the standard deviation, see if you add and subtract 3 standard deviations from that number, everybody in America, virtually everybody in America is in that range. Now, if you only go 2 standard deviations, you still get a large percentage of Americans. 2 standard deviations would be from here to here. And that's 95% of all the data is in that range. And then if you do the last one, only one standard deviation either side of the mean, then 68, roughly 2/3 of the people. So if you imagine starting here and going all the way to there, 68%. Now, it doesn't matter whether the data was people's heights, scores in tests, how many coins you got in your pocket, whatever it is, this pattern holds steady, which means that we can actually, only being told two things, the mean and standard deviation, we can actually tell an awful lot about the entire population. So let's suppose we do IQ. Well, if you have ever had an IQ test, the mean is 100 and the standard deviation is 10. Now I'm going to create one of these normal distributions. So right in the middle is 100, then 110, 120, and you finish at 130. Go back the way, one standard deviation, two standard deviations, three standard deviations. I can now tell you a lot about what percentage of Americans have certain IQs. For instance, if you take an IQ of 90, which is here, and you go all the way up to people who have an IQ of 110, which is here, and do you see that is one standard deviation away from the mean? So I can tell you in that range of IQs, you will find 2/3 of Americans. So there's a very good chance that everybody in this room, or almost everybody in this room, has an IQ in that range, at least 2/3 of you. Now, if you do an IQ from 3 standard deviations either side of the mean, which is from here to here, so that would be an IQ of 70 up to 130, you got almost all of them, almost everyone. As a number, it's been found that it was 99.7%. It also allows us to tell who outliers are. Anybody who is at the extreme ends of this distribution will be an outlier. And that means anybody who's 3 standard deviations or more away. So an outlier would be anybody who has an IQ greater than 130 and anyone who has an IQ less than 70. So an IQ greater than 130, that would be, like the Einsteins of this world, but actually I don't think his IQ was that high, but some really high IQ people. And an IQ 70 would be like football players. I got a dig in football players there and nobody even caught it, right? Well, not quarterbacks. Quarterbacks are very intelligent, but whatever. So we now have a test to see if someone's an outlier. And we can also come up with percentages of what people are in a certain range. So let's do that, an example of that. Suppose there was a test, and in that test, the mean in the class was 60, and the standard deviation was 5. And we'd like to know what percentage of students got between 50 and 70. Okay, take the number 50. Isn't that 60 plus 2 lots of 5? Right. Well, isn't the 50 60? Take away 2 lots of 5, and the 70 is 60 plus 2 lots of 5. What that's telling me is that this is 2 standard deviations from the mean, right? And what percentage of people lie within 2 standard deviations of the mean? Can you remember what that number was? Anyone remember the number for 2 standard deviations away from the mean? Okay, here goes to remind you then. If you do 1 standard deviation away from the mean, it's 68%. If you do 2 standard deviations, it's 95%. And 3 standard deviations, you got almost all, which is 99.7%. So in this question, what percentage of students got between 50 and 70? Since it's 2 standard deviations, we would say 95% of the people in this class had a score somewhere in that range. Now you could also ask, I bet this is another question. Is a score of 80 an outlier? Well, anyone want to make a prediction? Do you think in this class, if you got a score of 80, would you be an extremely unlikely number, an outlier?
Yes.
Agreed. We need to kind of convince or prove it by a property. So aren't outliers anybody who's bigger than 3 standard deviations? So anybody bigger than 3 times 5. So you'd have to get less than 45 or more than 65 to be considered an outlier. And 65, 75. More than 75 to be considered an outlier. And 80 clearly is. What this does is it gives us a way of deciding who outliers are, potential outliers are, without doing a value judgment on it. Yeah, that looks kind of extra big. I think it's an outlier. And now you can actually do a comparison. So let me show you an outlier question in 2 contexts. Class A, Class B. In Class A, the average was 50 and the standard deviation was 10. And in Class B, the average was 50, but the standard deviation was 2. And let's suppose in each of these classes, there was a student who got exactly the same score. Could happen. This student got 60, and so did this. Looking at this data, can you make a call on who, if any of those 2 are outliers? And secondly, well, let's do that first, and then I'll do the second one. Mean of 50, standard deviation of 10. Let's find out what the upper limit would be. Well, for Class A, isn't it the mean plus 3 standard deviations? And that would be 80. So for Class A, isn't that 60 just one of the typical scores that people might get in that class? Let's get Class B now. Still 50, plus 3 lots of 2, which is 6. Oh, can you see that this would be an outlier? So how can a class with the same average have a 60 as an outlier? Extremely difficult, unusual score to get. Yet in the other class, it's just normal. Anybody could get that score. What is the main difference between these 2 classes that's making this happen?
One assignment, one test might have been harder than the other?
Well, then wouldn't that be reflected in the mean being smaller?
Wouldn't the mean just be, well, I guess, yeah.
What's the only thing that is different between those groups? Because that must be what's causing it. Standard deviation, right? Now, if you have a standard deviation that is big, doesn't that mean in the middle you've got 50, but isn't there lots of variation so people get 60s and 70s quite easily, right? And in the other group, the mean is 50, but the standard deviation is tiny. Doesn't that mean that things don't vary a lot? So, you know, you get 52s and 54s and maybe 56s, but you won't get really too extreme a result. So this is just a measure of variability. It's easier to get 60 in a class with a lot of variation than it is to get 60 in a class where almost everybody gets the same score. That makes sense? Okay. So what is left? Well, I've got a really big, horrible diagram that I want to show you. And the book has much better versions of this. So you're just going to have to kind of watch this. What we have here is an IQ of 100 and all the IQs going up the way and all the IQs going down the way. And then it's split into little regions. And each of these regions has a percentage in it. So for instance, if you start with the mean of 100 and you go one standard deviation, so in this case from 100 to 110, 34% of people are going to be in that range. And it doesn't matter if that's 100 or whatever the mean is. If you do the mean and then you do the mean plus one standard deviation, which is basically from there to there, everybody has 34% of the data in the range, the mean plus one standard deviation. And from there to there, it's 13.5, and from there to there, it's 2.35. The result is that if you create one of these quite messy pictures, but if you create one, you can then answer more complicated questions like what percentage of people got an IQ between one number and the other. So for instance, what percentage of people get an IQ from 80 up to, say, 120? Oh, that's too easy. Let's make it 110. That's a little bit harder. Right, you start at 80 and you finish at 110. Well, the first piece of the cake from there to there has 13.5%. This piece here has 34%, and this last piece has another 34%. So you can add them all together, and I'll tell you in a few seconds. So you go 13.5 plus 34 plus 34, and the answer you get is at 81.5%. So if you've got this little piece of cake, I think of it as like a cake, all you need to do, for instance, is add up the pieces from whatever the start to the finish number that you want. So, you know, I could do 70 up to 100. I could do 70 up to 110 or 120. Just start here and add them up. These percentages are fixed. They don't change. Now, what might change is the mean and the standard deviation, like the numbers on this bottom scale. That'll depend on the story. But the way the cake is cut up is always going to be the same. Now, this mess at the top here, if you take the middle and you go everything forever to the right-hand side, that is 50% of the cake. Would you agree that 50% either side, it's cut into two equal halves? So far, so good. Now, for instance, if somebody went and said to you, okay then, how many people have an IQ greater than 90 in America? What percentage of people, adults? Right, you cover that up. Do you see it's made up of this and all that? Well, what I would do is I'd say, okay, this bit is 34. But I don't want to add all these pieces up because I know they all come to 50. So the answer is 84%. Are we good with what we've looked at so far? Any questions? Okay. Last chance. Then we'll move on to the next part of 6.1, are called standardized z-scores. Actually, everybody just calls them z-scores. So what is a z-score? A z-score is a number, and it's the number of standard deviations the data is from the mean. So there's a formula for doing that. The z-score is x, that's the data, take away mu, that's the mean, over sigma, the standard deviation. So let's suppose that we do IQ again. The mean is 100 and the standard deviation is 10. And let's suppose somebody got a IQ score and it was 117. That person's z-score would be 117, take away the mean, divided by 10. And that would be a z-score of 1.7. Suppose he had a friend whose IQ was 93. Well, the z-score is 93, take away 100 over 10. And can you see in this case, the z-score is negative 0.7. So a z-score is a way of calculating how far away from the mean in terms of standard deviations any particular piece of data happens to be. If I gave you a couple of z-scores, you should be able to tell a little bit about what the original data looked like. Here are 3 z-scores. We'll pretend it's the IQs again. If you have a z-score of 0, what IQ do you have?
100.
You do? Yeah. Agreed. If a z-score is 0 for a number, doesn't that mean that number is the same value as the mean? Does that make sense? Because take them away, that's how you get 0. If it is a positive number, does it not mean that the score has to be bigger than 100? Right, a positive z-score means you are greater than the mean, in this case by 3.1 standard deviations, but greater than means enough. And if it's negative, does it not mean that you're less than the mean? So that means you're greater than the mean, and that means you're less than the mean. Are any one of those 3 scores a potential outlier?
The first one.
And that's because its z-score is 3 or bigger. Remember, 3 or bigger is the magic number for deciding if something's a potential outlier. Now we can use these z-scores in quite a few ways. Let me show you one of the uses for it. Let's change the story. We're going to use it. How to tell who did better in a test. So like an, well, I know, like a SAT test or something, right? Now, let's have two classes. I'll call them Class A and Class B. And in Class A, the mean was 70, and the standard deviation was 10. And in Class B, the mean was 70, and the standard deviation was 5. And there were two people, one in each class, but they both got a score of 80. Yeah. In my last class, I think I called them John and Mary. And they were having an argument about who did best, who did a harder job. And John went and said, hey, we both got 80. We both did equally good. You weren't better than me, you weren't worse than me, you got 80. And his argument was, well, the averages in both classes were the same. And so getting an 80 in my class was just as hard to get as an 80 in your class. And Mary said, no, that's not quite the way it really is. Your class has a lot more variation than my class. It's much harder in my class to get really big scores in the test. Or for that matter, even small scores. Because the standard deviation is what, half the size of you. So how do we decide in a fair way is that you get the Z-score. So I'm going to get the Z-score from Class A. It's the data, take away the mean, over the standard deviation. John got 80, the mean was 70, and the standard deviation is 10. So he got a Z-score of 1. Let's do Mary now. Well, Mary also got 80. The mean was also 70. But the standard deviation was 5, and she got 2. And this is a truism. Oops. Bigger Z-scores are harder to get. Than smaller ones. So what that means is Mary did do better. It was much harder in her class to get a score of 80 than it was for John to get a score of 80. Does that seem a reasonable conclusion based on the information? Comfortable with that? Okay, let's do one more comparison one. Make it a little bit trickier. In Class A, the average was 50 and the standard deviation was 10. And in Class B, the average was 60 and the standard deviation was 5 again. But in this second test, John got 80 and Mary got 75. So there are 3 possible answers to this question, who did best? John did better than Mary, Mary did better than John, or they both did pretty much the same. That's the 3 choices. Any gut feeling for which one is going to be the result?
The same.
The same. Yeah.
I hear the same. I think it was Chris that said it, or maybe Derek.
Yeah, A is 30/10, and B is 15/5, which both equal to 3.
So they're both the same, agreed. Now, do you see we have now a numerical way to compare things that don't even have the same mean or standard deviation, yet we're still able to come up with somebody was about the same, somebody did better than the other person, or less well than the other person. That's a pretty cool thing. Now, I wish I had the data. I may actually have it around here. You know that in the medical field, you very often get blood tests and all sorts of other tests. And one of the things that they check you for, or they have a limit on what is exceptional and therefore should be worried about. Okay, does anybody know? I know part of the answer, but I don't know the rest. This is going to be your body temperature question. Does anyone know what the typical normal average body temperature for a healthy person is?
You know, Philip and Sarah,
98.6, I believe.
satellites are
Well, there's another conversation. I'm not sure if it's directed at me, but the mean is 98.6. And this I looked up, but you know the standard deviation is 0.6. So there's a little bit of variation. For all sorts of reasons, you could have a fever as well. Now, I'm going to do the mean plus 3 standard deviations. So that's 98.6. Add 3 lots of that guy is 1.8. And you put those together, you get 100. 100.4 degrees. And one of my other stats students who works in, I'm not sure what her job is, but she works in the nursing in a hospital. And she's saying that many of the people, the nurses there, this is like a magic number to them. If someone's temperature comes out to be 100.4, right, then they get worried. Right, that's too high just to be, you know, hey, you've got a chill or you've got a fever. It's not a really bad fever. Don't worry about it. You know, take some Tylenol and rest for a few days. But that number is considered the dangerous number to them. And can you see that it's an outlier? It's at the edge of really extreme. And so you can do that for any body chemistry thing. Potassium level. Find the average potassium level and the standard deviation in a typical person. Do this 3 above and 3 below thing. I could go the other way then. If you take 3 below, it's an average of that, take away 1.8. I'm not going to risk doing that in my head. 98.6 subtract 1.8, and you get 96.8. So at this side, we're talking fever, maybe infection. I don't know if COVID does that. It may be one of its symptoms. And here, could that be hyperthermia? In other words, someone who's been, you know, on a cold night and their body temperature has dropped to a dangerously low level. But see, these are the numbers that are the place where you get really worried. You wouldn't be that worried if somebody's temperature was 99 degrees, right? And you might not be that worried if somebody's temperature was 98, because that's just, you know, some people are a little bit cold, right? They're just normally, they don't heat up well. Are we cool with those questions? So can you see that Z scores can be helpful, and 3 plus or minus 3 standard deviations can also be helpful. Right, I'm now going to move to, good grief, at the time, things are shooting by, and show you some of the homework questions so that we can get an idea of, as usual, how the book tackles that same information. So with a bit of luck, double check that, not sure I'm on the right screen at all. Yeah, I am. So are you looking at essentially 6-1 homework? Okay, here goes. Which of any of these is a normal curve? One of them is A, B, C, or D. I could get lonely here on my own, so it's nice if someone joins in. A, B, C, or D. Which of those four shapes? Don't need to be curves. Curves isn't an issue. Which of these four shapes is closest to being a normal shape?
A?
Okay, well, you answered, that's cool. If I look at A, do you see a skew to the left? You agree? It's got a little kink to the left.
Oh, yeah. Would it be B then?
Well, let's go through them. Let's A, we're kicking that out because it's skewed left. Now, B is a bit weirder, but I'm going to kick that out for a different reason. It doesn't look like a bell. It's got a little funny kink here, right? It's lower down here in negative numbers and weird stuff. I'm going to kick out C. What's wrong with C?
Is the dips?
Yeah, isn't it technically got two extra little hills? So it's not bell-shaped. A bell shape is actually D. And you might think, wait a minute, that's made up of straight lines. It doesn't really matter that it's made up of straight lines. Has it got one hill right in the middle? Yep. Does it roughly go down equally on both sides so it's not skewed in any way? Yep. That makes it normal. Now, here's question 2. Here is a nice normal shaped curve. See, they draw much better curves than I do. And along the bottom, they've got 92, 94, 96, 98, right? The usual kind of 1, 2, 3 standard deviation thing. Only using this picture, would you agree that it is 92 is the mean? You agree? What's the standard deviation looking at that picture?
2.
Agreed. For anybody who didn't get that, you want to tell them how you figured it out?
You just subtract the first standard deviation from the mean.
Yes. Now, there a guy in the middle, sigma plus mu, right? Sorry, mu plus sigma, right? Mu plus sigma. Who's he talking about? What's the number?
94.
Correct. Now, that's my homework. Do you know your homework might say mu plus 2 sigmas? If it did, wouldn't the answer be 96? If it said mu plus 1, 2, 3 sigmas, do you see it would be 98? That depends on the question. Here are two normal distributions. One's taller than the other, that's fine. But they have that nice bell-shaped curve that they like. And they're asking you which one has a larger standard deviation. A or B?
A.
Okay, let's see why he's right. There's the mean. 2 units, 2 units, 2 units. You see the 3 steps. Here's the mean. 1 unit, 1 unit, 1 unit. You see it's to do with the mean to the next number, to the next number, to the next number. Because from one number to the next, that's how much a standard deviation is. And here are just a whole load of pictures where they give you a mean and the standard deviation, and one of these 4 pictures would represent what that would look like. Let's take this one. The mean is 15 and the standard deviation is 3. So from the center, don't you want to go 15, 18, 21, 24? So that makes it this picture. Do you see 15, add 3, add 3, add 3? Does that make sense? Okay, what percentage of area under a normal curve lies to the left of the mean? So if you took a curve and you drew a line exactly where the mean is, how much of the shape would be to the left?
50%.
Agreed. What percentage would be between here and here? Isn't that just another way of saying one standard deviation either side of the mean? And that was in my little table that's not.
34%.
One piece is 34, but go the other side, you get another 34, don't you? So altogether, 68. Now, if it was from the mean to one side, it would be 34. But that picture, I had 34 on each side, so I added up. Oh, this is an awkward one. It's a kind of weird answer. It's 3 standard deviations either side of the mean. What percentage is that? One standard deviation either side of the mean is 68. 2 standard deviations either side of the mean is 95. And so what's 3?
It's 100% because it's covering the whole thing.
It almost is, but it's 99.7. Almost all of it. There's a tiny little bit that's not there. That's why it's not exactly 100%. Because at that boundary, anything beyond it is the outlier. So there has to be at least space out of the 100% for an outlier to be there. And here's some more examples of that same thing. And there is that pretty picture that I can't draw. Can you see it's much nicer in color with all the details in there? When you're doing this homework, it might be a good idea. I know if you've got a printer to print this out, it's just helpful for counting things. And it goes on and it asks you the same kind of questions I did. Here's another practice one. Here's a third one. And then we get to this one here, question 10. At Burnt Mesa Pueblo, studies have been excavated and they've determined using tree ring information that the mean age was 1233 and that the standard deviation was 27 years. And then it basically asks us for what range were 68, 95, and then almost all. So I'm going to close this guy off here and come back in and show you what that would look like as working. Okay. 68%. Well, that's the mean, give or take 1 standard deviation. So that's 1233, give or take 27. So 1233, add 27, gets me 1260. And 1233, take away 27, gets me that number. Now, can you imagine doing 95%? Wouldn't you just do the mean plus or minus 2 standard deviations? And for what they're calling almost all, which is really 99.7%, you do the same thing with 3 standard deviations. And the next question that you can't see are pretty much the same type of question that we've just done there. Right, so that is 6-1 finished. We're going to start 6-2, try and get as much done as I can before I have to leave. Is there anything that we've covered in 6-1 that you'd like more information about. Okay. Anything in chat? Okay, I understand why Courtney's not joining in. Her technical issues, as unfortunately that's the way these darn things go, isn't it? Okay, so we're now going to look at 6.2. There are 4 sections in chapter 6, so this is us starting 6.2. We won't get it finished today, unfortunately, but we are going to at least get a start on it. So I've just got myself set up here. So let's do some basic calculations in z-scores. The mean is 20. Let's say the standard deviation is 4. If somebody has a score of 35, what would their z-score look like? Well, it would be 35, take away 20, divided by 4. And that comes out at a whopping 3.75. Now, someone had a score of 15, then the z-score for that person would be negative 1.25. So there's nothing new there. So far, so good. Now, let's reverse that question. Suppose I told you someone had a z-score and it was 1.2. And I asked you to find what the original data score was. Now, the formula that we use for calculating z-scores isn't really going to help easily with that problem. It's x take away mu over sigma. Just to remind you, in this question, the mu is 15 and the sigma is 4. Now, you could do it this way, and I'm only going to show you this once because there's an easier way. Couldn't you just say, well, the z-score is 1.2, so that goes there. I don't know what x is, but I do know that the mean is 15 and that the standard deviation is 4. And couldn't I just go and solve an equation the way I might have done in Math 99? So we are going to do that question in that form. Well, if I put this guy over 1, won't cross multiply work. X minus that gives me this. And 1.2 times 4 gets me 4.8. And then to get x, you just add 15 to both sides. And there's your answer. For this particular situation, to get a z-score of 1.2, you needed a data point that was 19.8, right? So you needed to be whatever that was. That's what you need to get in the test. Now, that is possible. I guess some of you might want to solve it that way, but here's a nicer way to do it. Let's just use a formula. X is the mean plus z-score times sigma. So x will be the mean, which is 15, plus a z-score, 1.2, times sigma, which is 4. And can you trust me that that gets you the same answer? So all you need to do is have a formula, know the numbers that go, plug them in, and you've got your x. So do IQs. The mean is 100. Standard deviation is 10. And we'll have 3 people. And these 3 people, all I'm going to tell you is their Z-score. But we should be able to calculate what their real IQ was. So, a Z-score of 1.2, a Z-score of 0, and a Z-score of negative 1.5. For a Z-score of 1.2, you use this fellow over here. So it's going to be the mean plus Z-score times sigma. In this case, it's going to be 100 plus 1.2 times 10, and I make that 112. I don't need to do a calculation for person B. I know what their score was because their Z-score is 0, right? So what did they get without even going near a calculator?
100.
Yeah. If your Z-score is 0, your score is the same number as the mean. Now, the next fella isn't too good. He's probably a football player again. His Z-score is negative 1.5. Doesn't that mean that his score must be less than 100? We're about to find out how less. Well, it's going to be 100 add, technically, negative 1.5 times 10. But that becomes 100, take away 15. Here's an IQ of 85. Different kind of Z-score question. We have 5 people. We're not going to tell you their height. What I'm going to tell you is what their Z-score was. Oops, can't have that. There. Which one of those 5 people is the tallest?
B.
That one, right? Who's the next tallest?
C.
Isn't E going to be in the middle?
Yes.
Then D, and then lastly, A. So I was able to put all those people in order of height, even although I don't know what their height is, all I knew was the Z-score for their height. But doesn't it follow the same natural order, right? Big scores mean you're tall. Negative scores mean you're really quite small, right, in relation to the others in that group. And one of these people I would even consider to be exceptionally tall. Who in this list of 5 people would be considered to be exceptionally tall?
B.
Because Z-scores are 3 or bigger are considered outliers, and that's how we decide if you are too big or if you are too small. Do you feel comfortable about that process? Now, I'm not doing the rest of this question, but suppose we then told you that the mean was 65 and the standard deviation was 2 inches. Couldn't we find out what the heights of every single one of those people would be using this formula, right? That makes sense? If I tell you the mean and standard deviation along with the Z-scores, wouldn't we be able to find the X's if we wanted to? We're just not going to. Now, this is me looking at the homework. This is question 8. We all got 73 in a test. And the mean in his test was 70. And the standard deviation in his test was 9. In his history. So that was what he got in his history test. He also took a biology test. And in the biology test, he got 70. But the mean in that class was 70. But the standard deviation was 10. And dead easy question. There's only 3 choices. He did the same. In other words, getting that score in this test was pretty much the same kind of thing as getting that score in this other test. Or the second one, biology, was better. Or the history was better. Now, we don't need to go into the number crunching yet. But what's your gut feeling? Do you think he did better in history, or do you think he did better in biology? Or do you think they're probably going to end up being about the same? So, whatever. What do you think? History, biology are the same. Logan, you got any ideas? Want to have a guess?
They're really kind of close to be able to just call it without doing the math.
Right. That's a good answer. So you're not sure because they're kind of caught. Right. Let's do the math then. For the 73 guy, right, it's going to be 73 take away 70 divided by 9, which I believe is 0.332 decimal places. And in the biology, the biology. Isn't the answer 0 without any work at all? So, guess what? He actually did better in his history exam. But it's not because that is 73 beats that 70. It's a combination between the two of them that matters. Do you know, I could make up a number where that history was, well, let's do it the other way. I could make up a situation where that biology score was less than 73, right? But he still did better. So let's see if I can make that happen. Let's suppose that he got less than 70. Oh, let's keep it as 70. But I'm going to change the mean now to 60. Right, that's the only difference. Right, he still got 70, but the class average was really 60. What does his Z-score look like now? Well, 70 take away 60 over 10, and that's a Z-score of 1. So isn't it harder to get 70 in this biology test than it was to get 73 in that history test? And you see in that news story, wouldn't biology be his better grade? That makes sense? So Z-scores are the fair way in which you should compare things, not the raw score, right? Not even the raw score with the mean, but the raw score with the mean and standard deviation. In other words, put them all together and get a single number called the Z-score. And that's your guy. He's going to be the one that will help you decide good, bad, or average. Right, so here's a question from the second section. Just keep an eye on the work here. College Physics Education Department offered an advanced first aid course last summer. The scores on the comprehensive final exam were normally distributed. Now what they did is they turned them all into Z-scores. Which of these students got more than the average? Don't overthink this one. Can you see that there's 3 of them altogether? I'm picking Robert, Juan, and Linda. Who in that class got the average? Agreed. See, Joel. And then who got below the mean? Well, won't that be these 2 poor guys, Haley and Jan? Now, in this second question, can you see you're just going to take all of these Z-scores and convert them back into raw data? So that's going to be X equals mean plus standard deviation, right? Z-score, standard deviation. Are we good? I'm going to move on to what's probably going to be our last topic for today. We're going to be looking at standard normal distribution. Now we have a normal distribution, but we haven't looked at what's called the standard normal distribution. This is what it looks like. It has a mean of 0. Just based on the numbers I've written at the bottom there, what's the standard deviation of the standard normal distribution? What's the standard?
1.
1. So the standard normal distribution is a particular, very special situation. It's an example of a normal distribution, right? Just IQs and so on, but it has a mean of 0 and a standard deviation 1. Why is this even important and given its own name? If you imagine taking IQ tests, right? This is what the distribution of lots and lots of people's IQs would look like, right? Look like that. Now, that particular one has a mean of 100 and a standard deviation of 10. Now, I want you to imagine that this is actually lots and lots of rectangles, right? Thousands upon thousands of people were asked writing. So these are all little rectangles, but they're so close to each other and there's lots of them, you can't see them, right? Couldn't I take every single one of these IQ scores and find out what their Z score was? Imagine me doing that? Taking an IQ of 100. Well, I could do that one. What is the Z score for an IQ of 100?
0.
0. Can you trust me that the other guys, and these are like signposts on the way, if you take a normal data set, right? In this case, it's IQs, but it could be height of people, weight of people, anything you like, but it's got this normal shape. If you take all the data and you convert them into Z scores and you make a histogram, it looks like this guy. So every single normal distribution in the world, if you turn it into Z scores, looks like this. That's amazing that that's true, because you can imagine what kind of distributions you get. Do you know you get some really thin, skinny ones, and you can have big, long, fat ones, and this number could be 20, and this number could be 100,000. I mean, you imagine the variation on that theme, but every single one of them, when you turn them into z-scores, all end up looking like that guy. That's a phenomenal property. It's not intuitive that you would expect that to happen, but nonetheless, it does happen. So suppose we were given a whole load of data, and I'm not going to do it because it would take me forever, but suppose we collected lots and lots of data on people's heights. Whatever, right? And I wanted to know, is this data got a nice normal distribution to it? Well, you draw a histogram, and can we pretend that the histogram kind of looked like that? And just for argument's sake, it was centered in 72, so we got that. And its standard deviation, let's say it was 5 for whatever reason. Can we be sure that this is actually a normal distribution or not? Now you can eyeball it, and very often you can look at it and you can tell the bad ones. If I did a distribution and it looked like this, would you agree that is skewed left? And so I can't use z-scores and all the cool stuff. If it looked like this, wouldn't it be skewed right? What's wrong with this fella? It's not unimodal. Well, as long as it's blatantly bad, I should be able to eyeball it. But what happens if it looks kind of okay, but you can't really be sure? Is there a way, a test that you can do? And there is a test that you can do. And I'm going to show you the picture of it eventually. This section is huge, so it takes me a while to scroll to the question I'm looking for. Darn it, they don't have it. Okay. Along the bottom, you take their normal score, right, their X score, and up here, you do their Z score. And you plot one against the other. Now, the real world, you're never going to get a perfect line, but would you agree that those dots are pretty straight? That's how you can tell that you've got a normal distribution. If your dots look like this, you see a bit of curve going on here, isn't there? Then it's not a normal distribution. And that's how they decide whether or not we can do, you know, like IQ tests and so on, that we can do all this cool stuff. Now, suppose I have a normal distribution. In this case, it's going to look like this. And I would like to know what x greater than or equal to 52 look like in terms of a z-score. So what do I mean here? Well, can you imagine that 52 is about here? If you want x to be bigger than or equal to 2, you're talking about everybody in the class who got more than 52 in the test. What would that look like in a z-score? Well, it would be greater than or equal to, oh, I need a mean and a standard deviation. Only looking at my picture, what's the mean?
$50.
Okay. Only looking at this picture, what is the standard deviation?
5.
Now, x greater than or equal to 52, which is this picture, becomes z greater than or equal to whatever the z score of 52 ends up being. So I'll do that over here. 52, take away 50, divided by 5, gets me 2 divided by 5, gets me 0.4. So you're going to find some questions where they get you to turn this information into that one. Now, what would that look like in my picture? Can you imagine 0.4 is about here? Now, whatever that percentage is, do you know this guy is going to be the same percentage? Which means that we don't need to have pictures of every possible normal distribution in the world, because there's an infinite number of them, with all the different little, you know, like the pie picture I had, that only had certain numbers in it, with every possible number in it. All we need is this guy. And we can take this information, turn it into what a z-score would look like for the same story. And this you can get because we have this guy stored in a computer. And the computer will tell us exactly what percentage is bigger than 0.4. And we don't need even work at it. You just go into Salt and say, I like to know what's bigger than 0.4. And boom, it's in front of you. Well, as I said, we're going to have to finish off at this point.